Hey, good morning, good afternoon, wherever you might be.
Yeah, hey there, Gino.
Hey, good afternoon.
Good afternoon. Happy Wednesday.
Hi. Where are you joining us from?
Actually, it's should have said good morning. I'm
Hey,
actually in the Chicagoland area.
nice.
It's funny.
Thanks for joining us.
I have a meeting with one of your guys, Isaac.
Yeah,
Oh, yeah,
Isaac. He sits right over there.
He has
Yeah.
been reaching to me, and I got a meeting with him in like 2 weeks. Go over just some of your stuff that you guys are working on.
that's
Awesome.
awesome.
I may be also on that meeting. I work with Isaac a lot uh on that too. Discovery
Awesome.
calls, potential new customers or people that reach out or that we reach out to, through connections and things like that. And again, like you said, hey, here's my problems. Here's the things I want to work on. Okay, do we have solutions to that? Right? Have we done something like that in the past, or are you looking down, the wrong hole? Because there's been people that called for all kinds of wild things. Hey, I know you got this vision, so I've got this problem. We handle lobsters and fish in my warehouse, and I want to know. I was like, okay, so first of all, it's not going to be our vision system looking at lobsters and fish in tanks. But interesting problem you have there. So it
Yeah, we've
happens.
got a lot of moving pieces, and I think we're more at that point where we're just kind of, I call it building the toolbox so
Yes,
that, when an opportunity comes, we have the right tool to apply.
you are you are doing the right thing that you'll see in my presentation about mistakes that people make that again in this computer vision world, but it's kind of based on all of my life experience of work and stuff where, you know, there's a phrase about the term assumptions and what it makes. And I won't have to go into on the webinar, but assumptions can be very deadly and extremely costly.
That's funny. I'm like, we should have added that slide.
Yeah, I use that one a lot. I learned that one as a young engineer. I assumed that this would be good enough. Oh, you assumed. So I guess all that school, understanding tensile strength and shear force and all that, it's just useless. You're just going to assume things like, okay, got the point. So,
All right. Um, Alex, real quick, do we have an echo going on? I don't have one on my side, but checking in with you.
no, I don't see an echo. So we're in good shape, I
Okay.
believe.
All right. Good. All right. Let's go ahead and get started then. Thanks for joining us for the fourth installment of Get a Grip, guys. Today we're going to talk about the 5 common mistakes of applying computer vision. So Alex is going to take you through computer vision, discuss some general assumptions, as he mentioned, and then also just explain, like everything else, why it's not a plug and play answer to all of your problems. My name is Lisa O'Brien. I'm your host today. A few quick notes before we get started. We'd like this webinar experience to be more conversational. So feel free to turn your cameras on because we'd love to get to know you a little bit. If you have a question, you can raise your hand. We'll call on you to ask it. If we don't end up getting to you, you can put it in the chat and then we'll get to you at the end of the presentation. And then lastly, today we're recording, so there will be a follow-up email to everybody, whether you attended or you weren't able to make it, but you registered, you'll get a copy of this. So before we dive in, let's welcome Alex, and I'm going to go ahead and let him introduce himself. So Alex, over to you.
Thanks, Lisa. Hey, everybody. Happy Wednesday. Hopefully, everybody's week's going good and all that good stuff. Let's jump in. So, today's webinar, obviously, they're in the title of 5 common mistakes of applying computer vision. Kind of compiled these from the most common ones that I've seen over the last 3.5 years, specifically, obviously, with Plus One's technology, which is computer vision in the logistics space. Although these are good general terms that I'll also pull from just my life as an engineer, my profession, starting in manufacturing, tier one automotive, and going through race car building and stuff. So there's some general stuff in here too. For anybody that's first time joining, don't know who I am, a brief introduction on myself. I'm an application engineer here at Plus One Robotics. Been here more than 3 years now. Built a lot of demos for trade shows, our customer experience center, our partners, things of that nature, discovery calls. I've done training for a lot of our partners. So we just got back last night from doing that, so that they can understand our technology better and how to use it. Number one there, the bullet point, I keep salespeople from selling things that are impossible. So I do a lot of those first time calls and technical fits. And again, I already said I pulled a lot of these mistakes from my own mistakes I made as an engineer, and applying new technologies to try to solve problems in the manufacturing world and also in the race car world. Although not so much with computer vision, but other pieces of technology, and then just things that I've seen where I've seen projects that fail or stall or have 1,001 change orders because mistakes and assumptions that were made and lack of understanding. So I hope to kind of bring those to light through this presentation, and then give some practical information on some actionable things to take from there, because I don't just like to point out the problems. So today we'll jump in and we'll hit these bullet points, right? So computer vision, it's a combination of hardware and software, right? You need a sensor that can capture, an image and data. Some of them are technically cameras, and we're guilty of it too. We call our sensors cameras all the time, but there's a ton of variety out there, both in how they operate and what they're good at and what they're not good at and who makes them. There's probably more sensors out there than applications that are unique to computer vision. There's so many. Another thing, computer vision is vision. That's why it's called vision, just with a computer. It's just a digital version of vision. So it has a lot of strengths. There's a lot of great things that it can do, but also has weaknesses that are just inherent to vision. The environment matters, but that specific question in there, how's the weather? There's other parts of the environment too, but I've seen this affect it. And the reason it does is because any solution that you're looking at would hopefully be a solution to a network wide problem, right? That has scale, right? That you're going to be able to solve this problem on a big scale, but it needs to be reliable, right? And it needs to be scalable. It needs to be something that works in this place and that place and deals with the changes. We'll go into a little bit 3D stuff, AI stuff. What's the difference in that? What makes one better than another? How do you understand if you need one type of computer vision software versus another, and understanding that? And then obviously, everybody gets a budget. They got $450 billion PO to go do advanced automation, right? All of us engineers just wishing for that. When it's time to buy, how do you know what to buy? How do you know about buying, right? Kind of like car buying, right? It can be an expensive thing. You got to be dealing with it for a while. So it's nice to have some points on that. Then we'll recap on any of the high points that I felt like I want to get the message through. And we'll take a quick pause before we jump into everything, because I know that computer vision is a term kind of like artificial intelligence. It's very broad in general, and not everybody has a sense of what it is. That top picture there on the left, which is, I don't know, Chicago or New York, something, but it's mini square blocks of a big city. That's computer vision. And then down here, thanks to Zivid with their awesome point cloud data on their cameras, tiny little Lego man and little tiny things that are like 1 inch big. Well, that's also computer vision, right? It's a very big, broad, sector of research or studies, right? Some of the bullet points on that, just again, basis here. It can be 2D stuff. So 2D is what you're looking at on your screen, right? That's RGB, just a color image. It can be 3D only, just point cloud data, no colors, and just do there. It could be 3D and AI and color, meaning a combination of a lot of these different things. There are 5 components. Again, not always obvious, right? People think it might just be software. Well, what gives it to data, right? So in the logistics world or in robotic space or advanced automation, where we're going to be spending our time talking today, you're going to have a sensor, and it's RGB and depth sensor. The cables that connect the sensor to the computer, there's obviously some onboard stuff now that's unique use cases, but yes, cables are super important. There will be a computer, right, that houses the software and does all the processing and communicates back to different things, and there will be the software on there. And controlled lighting is a point that a lot is missed. We'll go into greater detail on that. Obviously, you can read the bullet points there, but if there is an external computer and you are dealing with, advanced vision systems, whether it be 3D only or 3D and AI, like, pick one like our software, you're going to have a powerful computer, right? Because you're not going to wait for 2 minutes for it to go give you the information back on whatever it was supposed to do. Things have to be able to happen quickly. So now let's jump into the first thing. Sensors and cameras. I say it all the time. There's more options than there are eyeballs, right? There's a ton of sensors out there. Some really great ones, some okay ones, but they have specific reasons why they built them. The ones that I'm most familiar with are obviously the main ones that we use. There are some other ones in there through the past, and I'm sure there'll be all kinds of different ones in the future. But we use an Intel RealSense on two options that we also use an Orbeck camera. They're different. Obviously, says LiDAR there. The other one I didn't put, but it's a stereo camera. So we use them for different applications because they have different qualities, pros and cons about them. We'll go into that a little bit too. And I'm going to run through this a little bit quick, guys, because I got a lot of slides and I don't want to eat up everybody's time. One point I want to make here, again, just if people aren't familiar with it, RGB, it's your computer screen. It's just an image, a picture. The D, because you'll see these sensors called this RGBD, is depth. So that means it's got a 3D side. So it looks cool when they do acronyms, right? Everybody loves acronyms. So the 3D data, right? That's the depth part of it. There are three common types to common ways to calculate or to measure that. Stereo cameras, which is like your eyeballs, time of flight, which there's a few versions. Primarily, we use LiDAR, and then there's structured light. What you see here on the top, I like to show this point, right? Got a poly bag here on a conveyor, right? Like a parcel induction application. And on the bottom, it's the same conveyor. It's maybe a different poly bag, but it's a different perspective. So it's like, oh, well, both these cameras, they're just in different spots. Well, the truth is they're actually both these cameras are directly above that package, right beside each other. There's the D415, and this is the L515 down here. Kind of see a little difference in how they look, and that would be because the D415 is a stereo camera, but it also uses an infrared pattern to help with like flat items and things of that nature. And I'd like to point out the two little arrows down here. That's not a shadow, right? There are no shadows here. I know this system very well. There's no shadows on it. That's just where there's no data, right? So it comes out black. And that's this point. Things that are in the field of view seem like, oh, you can see it. You should know what that is, but it is only where the data's at, right? It's not like we know that there's something there or not there. There could be, a little ring or something down there that you couldn't see. And the other point I want to make on the 3D data, without jump into technical into stuff, is that you're going to pull multiple frames. So just like a movie's running whatever 24, 30 frames per second, the camera's constantly reading out. With pick one with our technology, you say I need a pick point or verify that this package is not too big and is one package and should be inducted onto a sorter. You're going to pull subframes. So the software needs to be able to handle the variations between those frames because point cloud data is kind of jiggly, right? It moves and it changes over time. We'll get into that a little bit later. But you need a software that's robust enough to be able to handle that and deal with it in the real world and deal with it quickly. This is for anybody who loves getting into the engineering of it. I won't go down deep in the rabbit hole here, guys. I know this is pretty technical or can get very technical, but I think it's important if these are, technologies that you're looking to apply and you're looking to solve your real problems, that, a background understanding of how they operate, I think would provide a lot of value in just in your research and understanding it, which goes into some of our later points. But stereo cameras calculate with Pythagorean theorem, right? They take pixels, they pixel match them. This is kind of a nice graphic of how that operates. And then they use Pythagorean theorem to say, well, how far away are you from my cameras? And looks at two different images and figures out how to make a 3D world out of two 2D images, which is kind of how your eyes work. There are big pros to that, and there are cons. I've got an easier graph to follow than this, but essentially, stereo cameras cannot operate at very long distances, and that's because pixels don't move very far at very long distances. There's a lot of cool things you can do covering up your eyes and stuff to get this understanding a little better, but it is a calculation, not a measurement. And then LiDAR, or any time of flight, is different. It is a measurement. It's measured off speed of light, right? And it takes X amount of time to go from here to there. And in that time, I know how far the light went before it came back. Obviously, some benefits in that since it's a measured thing versus a calculated thing. And there's some weaknesses in there too. Specifically that you're relying on the in the case of LiDAR, the laser to go out and come back, and things can absorb light, and light can be refracted and reflected, and in weird ways. So that can make for an issue, or just make other difficult parts of using it. I've got in there in that point. It works best when it's pretty much perpendicular to a surface, right? And that's just because things like to bounce at angles. So if you like throwing the baseball or whatever against the wall, right? You're waiting for that laser to come back. So things that are going to be at really weird angles and have a lot of that physical requirement to them, potentially time of flight sensors are not the way to go. Just as a heads up. And then as well as dark items or black items, or just things that absorb light, right? Things that are dark or black are that way because they didn't reflect any light, right? They absorbed all the light versus white, which is they did reflect all the light. And this is for the non-engineering guys, although maybe the engineer guys will like this too, on a little easier way. Again, just with LiDAR and stereo, specifically since that's what I'm most familiar with, so I can write about it easier. But how they operate, right? And some of the kind of pros and cons or ways in which they're good and ways in which they're bad. I do put down there in the note that I think everyone should take note of. If something affects the RGB, so if something affects the picture, the colors, it affects the performance of the AI. And I'm not going to say that it makes it terrible or it messes it up. It just doesn't give the consistent result, right? It can give a different result. Could it still operate? Potentially, yes. But that's not really what you're looking for when you're, again, trying to apply a technology to scale over a problem that's through your network. You want to have consistency. You want to know that if it works here, it works the same over here, right? So things that can affect RGB, like solar interference, motion activated lights, that would be they turn on and they turn off, and maybe somebody drives a forklift by and they turn back on again. Those type of things change the colors of the image or the colors of the item, just like it does with your own vision versus walking into a room where it's kind of dark and then everybody turns the light on, and then you can see all the colors and the things that are going on. Some of the key differentials that we'll put here is solar interference, right? Sunlight definitely affects stereo cameras, right? It's not like they're immune to this, but it does not affect them nearly as gravely as it does with a LiDAR or anything that's going to be using, a form of the spectrum of light that the sun has a full spectrum. So when the sun hits it, it's more powerful than any sensor that's going to blast any type of lasers or infrared or ultraviolet or any type of thing that they want to use. The sunlight will destroy it, and you'll have no 3D data. So the sun is very, very treacherous to LiDAR sensors. Um, but again, if this will be sent to you guys, but this is a really nice, this quick guide that dives into a lot of customers in the past and other partners trying to understand in a little greater detail of in what situations things will work and what situations that they won't, so you can understand when you design and when you're thinking about your scale. So, what's the mistake that people make when in this specific regard with sensors? Is that they choose a sensor or purchase or apply a sensor that's ill-fitted to the work that's going to be done. What I mean by that is that the weaknesses in the sensor or the cons aspect of the sensor are a large part of the work that is to be done. A great example of this is using like the D415 stereo sensor. It's got a pretty solid working range for a small stereo sensor. Maybe say you could push 60 inches, 50 inches is pretty solid. But what if 20% of your work that you're going to expect this machine to do or for this vision system to, analyze is 80 inches away? Well, then 20% of your work is in a working range of the sensor that's really poor. So you're going to get really inconsistent and bad quality results, right? It's not going to be a good solution. Lighting, the same thing. Obviously, the solar being a big one on LiDAR, right? You put it in here, but between 8 a.m. and 10 a.m., the sunlight comes right through the bay door that operations teams like to leave open and catch the breeze. But it's right on the area that this decal robot's at. So in the morning, the decal robot can never see anything to do any work. Um, these type of factors I've seen firsthand, with, the years that I've been here and, dealing with some customers and, things that are going on there, as well as mistakes that I made in my life. Um, there also is in this fourth point, what I mean by the lack of capability creates exceptions. Exceptions are anytime that the system didn't just do what it was supposed to do autonomously. And the lack of capability is a combination of that last chart, right? You got too many little parts of these factors that the sensor cannot overcome. Thus, you get performance that's unacceptable, right? Too low quality or too low throughput or too low whatever the KPIs are. And a big part of that, from my experience, has been, I call it suboptimal research, just lack of knowledge, right? You see a sensor, they tell you it does this thing, they show you some video of it, or you do some research, and then you apply it. You do some shopping around, and then you go, oh, I'm going to set this up, and you set it up, and then you realize it doesn't really work right, and there's too many situations in which it doesn't do what it's supposed to do. So hopefully, like this webinar is one of those things. So when you're looking at sensors, a little research on your team side on understanding the sensors is very helpful. So computer vision is still vision. It's still vision. That's why it's called vision. It's just a digital version of that, right? All ones and zeros, let's say. So lighting is very important. And again, vision's a pretty easy one to talk about since, we all have vision here and we're all looking around at things all the time. Things that are super bright, right? When the sun hits you in the eye when you're driving, you flip down your sunshade, um, things of that nature. Or things are really dark, you can't see anything. Vision, computer vision is vision. There are hardware solutions around some of that, but there's two core pillars of computer vision that any computer vision scientist can sing to the end of time about issues. And it's uncontrolled lighting or varying lighting, which is why I have this image over here, which you can see the original one and then all the different lighting changes, and then blurry images. Um, Blurry images is getting less and less of a problem as things develop and get better. Obviously, here at Plus One, we work on that a lot, with our AI and just our vision software and being able to deal with blurry images, but it's by far less than ideal, especially when you're trying to like classify things. Like we say it's a poly bag or it's a box or, whatever that may be. It's a palette or a slip sheet. The blurry images are errors in data that have different numbers than they should, essentially, that the AI doesn't recognize. So having good clear images and having consistent lighting means that you get consistent performance, which is why I put the point in there. The most robust systems that I've ever seen, our systems, including other, advanced vision systems out there, whether they be attached to a robot or not, have their own lighting. They have a controlled lighting. You do scan tunnels and things like that if you're in the warehouse space and you're looking at sorters. And the reason is because the proper lighting, so the right color of light, the right lumens, so the right power level, creates a very uniform um, lighting pattern throughout and eliminates shadows. That's really important because shadows are just another variable that the system must have to account for. And like anything else in nature, it's relatively infinite. So it makes it rather difficult to get consistent long-term performance. And then I go into a little bit with this picture. Again, we don't have to bang through all of it. You are in one of my training classes right now, but diffuse lighting is in almost all applications where you're going to find the best type of lighting, for computer vision, diffuse lighting, like that. Spectral reflection, if you guys are into microchips and making those, maybe you'll like that lighting a little better for quality checks and stuff. But diffuse lighting is one that's very important. And that means the lights that are on the system that are shining down, right? They're diffuse lighting. So when the light hits whatever the item is or whatever you're looking at, it comes back in that same array. And for my visual learners and anybody else, I think this is a little test that I did a while back, discussing some stuff with a customer, and this is an L515, roughly 10 feet away from this pallet, and I just put it on a tripod, took some pictures, moved it over, took some more pictures, and made this little graph. But I want to point out two things in here. First, you got this like glass jars with these little metal lids, so you're losing some data there, right? All those dark spots are no data, right? It shines off and blasts in different directions and doesn't make it back to the sensor. But also, I got this Gatorade back here. But I just moved the camera 2 feet. And from the perspective and the angle, right, that the lasers are bouncing off stuff, I can't see the Gatorade at all. And basically, can't even see these obviously, 12, jars here. Basically gone. Not to mention that I can see nothing back here, right, wherever you see that grid. But over here, I'm catching like some stuff kind of far away, and like there's some pole over here. So I bring this up just for the specific point of driving home the fact that computer vision is vision. Obviously, our vision doesn't have a problem standing out here. I could see the whole, warehouse, or back there in the R&D lab, just fine. But computer vision still has limits. It has some strengths over people vision, but it has some weaknesses too, like this. Oh, right. Human vision is 3D and intelligence. I tell people that all the time. So what is what we're doing? What is like, plus one's software? Pick one. Well, it's 3D and artificial intelligence, right? I've got a specific example in here because it relates specifically to these pictures, but it's just talking about how our system operates, right? By the AI segmenting thing, finding all the edges, and then comparing that to the 3D data because the 3D data is real, right? That is the real world. This is where it exists in the real world and where all the shapes are and yada yada, right? And then that's got to get analyzed, processed, and cleaned up. And you can see up there on the top right, the AI is pretty confident in all those. It's like 99% sure all those are boxes or whatever it's saying that they are. But it'll give that out right as a score. And I think that the image does a good job of showing this. But specifically, I like to talk to people like human beings are incredible. That's why we say robots work and people rule because these exceptions come through. We have Yonder, Human in the Loop, which was like the last webinar. People can look at it and say, exactly, this is what we need to do. It's easy, right? Harder for computer vision systems because artificial intelligence still hasn't quite caught up to people as much as the media may say it has and hasn't. And so how does that translate, into an actual, say, computer vision software, right? This is generally how it operates in most all cases. And then the last one is in calibrations. The vision system most commonly is separate than whatever piece of machine is going to move, whether that be a robot arm or whatever else, or if it's not moving a machine at all and you're just using it for the vision aspect, whether that be a quality assurance thing or some other process related deal where you just want the vision. It needs to be calibrated. It needs to be told where the world is. And in most cases, again, most commonly, if you're working with a robot or a piece of machine, you'll calibrate the vision system with a target, and then you will calibrate the machine to that same frame of reference. And I only put that out there because a lot of people don't realize that. They just think you put a camera on here and now it can see things and it should just know. Unfortunately, not that simple yet, and might not be for a little while. So don't hold your breath. Lastly, and again, we're getting out of the super technical stuff. We're finishing finishing it up, but I think it's very important as we get in later on in this webinar and understanding this background first. So, computer vision software, it can be developed to do all kinds of stuff, right? I'm going to show all these pictures in warehouse situations because that's where we reside and operate, where I'm most familiar. But you can do a ton of things with it, like that first picture we showed, map an entire fly drone around and map entire cities, or look for the tiniest nanometer of imperfection on microchips, however you want to say, or, classify people, or, do all kinds of other different things. But successful software, it has to manage the real world. And I say that in the sense of you're not going to have like laboratory and perfect conditions and everything's not going to come in perfect. Like this pallet's an example. Why are like all these beautiful ones lined up nice in a row like they're supposed to be? And then everything else on the left side's a super mess. Maybe the next pallet will be perfect. Maybe it won't. Maybe it'll be worse than this one. But when you're looking into these advanced vision technologies, like understand that, you know, they have to be robust enough to handle this, right? And, being able to prove that out is very important. Um, we'll jump through. So the mistake that people make, the biggest one, they can forget that AI does not equal omni intelligence, essentially, right? It's still vision. You still can't look at an item and see how heavy it is, right? Like it still is just vision, even if it has AI on it and things of that nature. Um, and that's forgotten, right? They see some really cool videos, whether that be whatever it is, even humanoid robots, right? There's still these real limits in what is capable there from a technical perspective or even a hardware perspective. Not considering the lighting changes. I know I made that example earlier, which was from a real situation some years ago when I was here, where when we did all of our testing and all of our acceptance testing and everything, all the bay doors are closed. And then when they got into operations, I guess the weather changed. It got to be fall time and they liked having the doors open and they were shining right in on the depalletization system at this facility. So we ended up having to put some coverings and stuff on there to protect from the sun and resolved it. But not considering those as you look out to scale is can be costly endeavor to not do. Specifically, go over that point twice, right? The sunlight, motion lights, barcode scanners, maybe not such a critical issue with like our technology specifically and how things are set up, but vision systems in general. I mean, I've even seen in my life where barcode scanners that are on one system and the other one's just at that right angle somewhere else. When they get in a situation where the timing's just right, they interrupt each other's scan, right? So understanding that barcode scanners and things of that nature can affect vision. Um, I point out the point earlier too that you can't solve everything with vision. Can't see how heavy stuff is. Showed the image there that in certain situations, things that are really there, you can't see them, right? They're like that. You can't see my other hand, right? I cover it up. Can't see my fingers. Still vision, right? It's not like superhero, Superman stuff. The environment matters. This is a short section, much less technical. So if everyone's tired of the technical stuff, sigh of relief for you guys. If everyone loved it, sorry. So that's the question, right? Where is your network? Where does it go? How big is it stretch? And how big is the problem that you have network wide? Because the environment can change a lot on computer vision. So I got a cool little picture up there from just somebody's own testing, right? Nice there, but you can see it's the same piece of hardware in the same tunnel, dealing with the same lights, and yet look at how different everything ends up looking on the exact same piece of hardware, looking at the same car in the same building, just with changing the environment around it. Specifically, I point out to cold environments with humidity or going in and out, like if you have like mobile robots or some type of mobile system or gantry system where the sensors are going in and out of a really cold environment. Doesn't have to be sub-freezing, but cooled environments, and then moving into like humid environments or non-cooled environments that humidity will form on the sensor potentially, right? So understanding ways to design and protect against that or use hardware that's capable of doing that is important. Same as the same problem as hot environments, right? Computers, sensors, all these things are electronics. Most of them for industrial stuff are fanless, right? So if you put them in really, really hot environments and they start to get into their own, let's call them overheating protections, like laptops and stuff do, they'll slow down. And potentially the vision system's timing is critical to the overall performance or process that you're trying to do. You could think of barcode scanning as a great example of that, right? If the barcode scanners are supposed to reply back the barcode in 50 milliseconds and they're starting to get so hot because of the environment that they're taking 100 milliseconds, perhaps the sorter isn't, getting the barcode stuff in time and it's just saying, oh, well, I don't know what item's on here, so I'm just going to take it to the jackpot or the hospital. Like understanding the environments that you're going to run into in that regard are important too, even though we may not think about it all the time. Dusty environments. We live in dusty environments, especially in our warehouse space, dealing with so much cardboard and other types of packaging. So we have PM schedules in place, whether we're doing them or our customers are doing them or however that's set up, where you just take a little Swiffer duster and clean off the sensors, whether it's every day or once a week, just depending on it. But it's on there. Hey, if you're checking the filter and you're checking this hose and you're just doing your basic checks, take a look at the sensor. Oh yeah, it's really dusty. Let me clean it off, right? So it's also dealing with vision, just like us. So dust affects it just the same. And then motion activated lights, not such a big deal anymore. I think there's still a lot of people that are aware and understand which facilities do and don't have motion activated lights and how those are controlled and orchestrated. But it's interesting how many times that we've scaled out through there through different facilities at the same customer. And some places have motion activated lights where the system's going, and some places don't. Right. So again, as you scale out the solution, so it's important to understand those variables through the network, which is the point of the mistake, right? People don't necessarily look forward enough. Where if you're trying to solve a problem, and if it's the only place that the problem exists, fair enough. A lot of times we're trying to solve problems that are network wide, whether that network be in North America only, or whether it be globally, or just North America and Europe, or North America and South America, or Central America. Like the if I solve this problem here in Toledo, the next place that really needs it, that really, really, really needs it super bad is, I don't know, Johannesburg or Sydney, Australia or something. Like, so what does that look like as you start to go through there? Whether that be, environmental changes from the standpoint of, hot and cold, or whether that be inside of the warehouse specifically in the type of material that's going to be there and the way those things are structured. So, like looking at that in the long term early on is very helpful as you start to say, we have solved it and now we can scale it. Um, so knowing hardware, right? A lot of that have specs. They'll tell you the minimum operating and maximum operating temperature. And if it's, something you need to be tested, it can be tested, but it should be understood. When over dust, right? So preventive maintenance is a pretty easy way to do it as long as the system's designed in a way that you can get to the sensors easy enough. Otherwise, you may need to do something else. And my great example for this, which I say all the time, solutions that work in Antarctica are overkill for Aspen, right? It's a lot colder in Antarctica. But if you're trying to keep something warm because it's in Antarctica and you bring it to San Antonio, let me tell you, you're going to be in a hospital because it's hot down here. All right, I need to keep going because we're getting pushing on time right here. 3D only, is that all you need? Do you need AI? Like what's the difference between the two? So I'll go through the pros and cons, and I'll go through this rather quickly since we're pushing on time. 3D information doesn't need training. AI stuff needs to be trained. You need to teach it what things are, so then it sees it, knows what they are. Um, there are depth and color channels on 3D, so you could use RGB as well, or you could just use depth, which is what you see there. The AI side predicts on 2D images, so it just needs the image. There are some unique cases where you can use AI on 3D data, but rather unique cases that are out there for that. Um, with 3D, a big con is you can double pick, especially items that are like right beside each other. Like the 3D data says, oh, that's all one item. Whereas the AI you can see there in the other image that it can predict and understand the items are overlapping. 3D data is less sensitive, more robust, right, to any type of external changes. Not immune, more robust. Whereas AI is generally more sensitive, especially to lighting changes because it changes the way the picture looks. And then 3D is less data to process than AI. So if you don't develop your AI well enough, or if the systems aren't there, you're going to see bottlenecks on processing time on the hardware. And we'll jump to this one quick as well, which is, again, if you guys haven't hopped into Robotics 24/7, the RAC 2024 conference, one of our colleagues, Dan Grolman, he talked in depth about this topic, specifically pertaining to human in the loop, pertaining to our approach, but he did a great job going over this. And it's, so if it's something that interests you, you could look that up and watch that webcast. But these are the steps that go through it. I like to put out two of these, overfitting and underfitting. Again, background understanding what's going on. Overfitted means it's really good at all the things that it knows about, and but it knows about, it can't deal with any changes in that. And then underfitted is it's just not very knowledgeable about anything, but they never generalize, which is just the computer vision or AI way of saying scaling, right? Where it can work across a wide variety. There's a lot of limits to the training, put them in those points there. But lastly, more training does not necessarily equate to a better performance. More data doesn't mean, oh, it's so much better now because I added 100,000 more images. It's it's an it's in it's a trade-off always, right? Not always, fair enough, but it's a trade-off in that you can get better at one thing, but you always need to do regression testing to make sure you didn't get worse at something you were already good at. So there's a balance and a nuance and a knowledge of understanding on how to train and what to train on and how to build that architecture that are critical in the long-term success of the vision system in the warehouse. And this is a super tiny picture of what a neural network looks like, what AI looks like. I've got some technical points in here. We don't have to go through them all. The biggest point I like to make on this is that the input is obviously a picture of George Washington. It goes through here. It does all the things there in the bullet points, and then the output is George. And I always joked about it because this was in some old class that I took this image, and it says George, and it's like, well, why doesn't it say George Washington? It's like because the AI was only told that to know it as George or Ben or first names, right? So the AI can be knowledgeable, but only as knowledgeable as what it's trained to be knowledgeable on. So this goes through some of the technical on how that operates for people that are interested. But in the sake of time, we'll jump. The mistake is people hear that it's got AI and they think, oh, awesome. I'll just throw this on here and it's intelligent and it'll just solve all my problems. But just because it's powerful, like these 10 trillion calculations per second, this is a totally reasonable, this is a high end system, but this isn't like supercomputer level. Oh, you could go buy stuff like this right now, like our systems, right? But it doesn't mean it knows what it's looking at, right? Or that what it does know about what it's looking at is correct, right? Especially in the warehouse. things are in constant flux, right? And most of our, logistics people are not controlling the packaging. They don't get to decide when Doritos changes the Doritos box around or goes from, red cardboard to brown cardboard. It goes from, this size to that size. They're in constant flux. Obviously, we've been doing this for a while. And we have a lot of general models that apply well over these problems, but we always have a cadence to the training of the AI models, right? And so it's important that you understand that that's going to be a requirement. So the failures are that package distribution is not considered. I've seen this many times where it's really looking at the problem and there's like, okay, this is specific big boxes that are the problem in our decal deal. And then the solution is only there, right? It's only in that. But the distribution throughout the network was not considered well. Um, Not understanding the edge cases that can get to a robotic or an automation or a vision system, right? If you don't know the weird situations that can occur in the process, it's very difficult to have a robust system. Last point is that there's not a process for continual learning, both either on the vision side or on the team side, on the internal side, of your company. So it's just time to buy, right? Because this is how I feel. Whenever I got a purchase order, I was always going trying to buy something uh, at the manufacturer plant or race car parts, which would maybe more fun to buy. You need a checklist. This is not an all-in everything you ever need to know checklist. This is, you know, the bullet points that I could fit on a slide with a reasonable size text on that. But I think it's a good starting point and hopefully can give you some kind of springboard to kick off of as you start to explore this with advanced technology. Vision system or potentially otherwise, I think it's relatively general. But if you're trying to solve a problem, the assumption is it's a network wide problem or it's a big enough problem more than just right here in this one specific place in this one specific instance. And if that's so, make sure that that is going to fit across the scale, right? I've seen countless times in my own life from mistakes of it solves the problem here in Texas and I take it back up to, Kentucky and we're going to put it in this warehouse and it just doesn't work with their process or their environment or their machine or their layout. And, then we're back spending an extra, $200,000 modifying it out to make it work. So done that. Don't forget about the environment. Ask questions about the environment to your team, right? Your operations teams and stuff, they know about their environment a lot. They can take pictures, they can tell you about it, they can laugh about how dusty their place is. And the next place says, no, we're not dusty, but it gets cold in here in December. And understanding that. Keep the total cost of ownership in mind, not just upfront costs. This can be a little bit difficult, but it's something that the pursuit of understanding that is very valuable. Customer support. I will not stress that enough. Customer support. If you've got integrator partners that you worked with for years and they provide that customer support, you know what I'm talking about. But it's very important throughout the life of using this technology. The distribution of the product, thoroughly vetted and understood. Make sure it's good data. Make sure it's right. Really understand it well. The better you do that, the better all these computer vision systems will operate for you. Edge cases need to be understood how they need to be handled, not just that which ones show up in the weird ways and how does this situation need to get resolved by the process, either through your network or at specific sites. That way that the automation is supporting the process that the operations teams there need. And I'd say just like an interview, ask hard questions and history of how they've dealt with their own problems, and dealt with like I said, like we did past a fat and then 2 weeks later we're not picking anything. We go out there and it's because that they got bay doors open. So how do we resolve that? So that we didn't tell them, hey, close those bay doors, right? It's their warehouse, it's their facility, it's their team doing the work. So we need to make sure that we're able to be capable of resolving that for them so they can, work in the environment they want to. Uh, and proof in the real world is always over anything in a lab. And I build demos, like I build the trade show demos. I run the experience center here. I go at customer sites, and they're fantastic. And there's a lot of value in there because we're in an environment we can sit around and talk and do things with the system and show off stuff. But if you're really looking out in today's time, today's world, real world use cases, real world scale with real customers always triumphs anything you see in a lab. It's not always possible because sometimes you're doing some crazy cutting edge type of stuff, but anytime that you can see them in the real world, it's so important. And I've seen that discounted before. This is why I put it in there. Well, they're depaling dog food bags. That's not what we got, or the opposite. Well, it may not be the exact item that you have, but it's in the real world and they bought 40 of them and they got it all through North America and Europe. So obviously it works from them. Maybe talk to that customer and understand why it does work for them, and you can use that as a comparison as you start to pursue these efforts. So I went through that pretty quick because I had a lot of slides. And it was pretty technical. So what was I talking about? Computer vision's hardware and software together. Um, Technically, right, you could have companies that just sell software or just sell this or that, but there's a combination. You have to acquire the data and you have to do something with it. Um, More sensors than I could possibly ever list on here. But if you're looking into something, right, you could do research on your own. But if you're looking into something, understand what sensors that they're using, and what their approach is with them and why they chose those. So you know the pros and cons of each of them, right? Stereo's got strengths, LiDAR, time of flight's got strengths, structured light has strengths, but why would you choose one over the other? Computer vision's vision, just like anything else. I tell people all the time, you can't see how heavy something is. And AI knows what it knows, but it doesn't know what it doesn't know. And depending on how you trained it is depending on how it could learn in the future. So understanding, to that extent of where a company is at with that, if it's an AI powered vision system, and how do they deal with those changes. North Pole to Death Valley, my favorite phrase. I've never been to the North Pole, but I've been to Death Valley and it was hot. But it's scale. That's just a scale question. Where are you going to go with this, and what are you going to be like, and what's the environment going to be like, and how does that deal with things that maybe you need a different type of power cable because you're in North Pole and it's super cold and needs to be insulated, but things of that nature. Get you a pre-purchase checklist. I mean, everyone's bought something expensive in their life, whether it's cars or houses or investments, right? There's a list you go through. The same way here. The more that you have something like that that really touches all the points and things that you need to understand from your KPIs and your requirements and what your operations teams needs network wide, the more that you can use that over and over again as you evaluate your options. The work that is to be done matters more than anything is something that we believe here at Plus One. Um, Even all of our computer developers and our software guys are the same way. They see it hack on the software, and like, okay, go put it on a robot. Let's make sure it actually picks this thing right. Looks like it does on software, but did it actually do the work? It's the most important thing that you can consider when you're evaluating it, because what you're trying to buy is a solution to a problem, not something that looks really cool on a computer. And lastly, my sense of humor: the sun is not your friend. And in the computer vision world, at the beach it is, right? When you're hiking and playing golf or whatever, it's your friend. Not in computer vision world. But now that everyone's asleep from all
Right.
my technical garbage,
That was awesome, Alex. Thank you so much. Does anyone have any questions? I know we're at time, but if someone's got one, we can fit one in. I didn't capture any during the presentation. Okay. All right. Well, if you think of anything after this seminar, feel free to reach out to either Alex or myself. Alex, if you want to advance to the next slide, one of
yeah,
these
for
has
sure.
our information on. Okay, so this is our next webinar. If you enjoyed this today, we'd love to see you again next month. So we do these on the fourth Wednesday of the month. The next one is on October 30th. You'll see the link out on LinkedIn as well, and you should receive this in your email when we send out the recording too. And let's see, go ahead. And then also, we've got a really busy schedule in October, so there are a lot of us that are hitting the road. You'll find us at the AMR and Logistics Conference in Memphis. We'll also be at the MHI Annual Conference in Marco Island in Florida, the Next Gen Supply Chain Conference in Chicago, Parcel and Post Expo in the Netherlands. So if you're going to be there, please let us know because we'd love to meet up. And here's our contact information. If you do have any questions, feel free to reach out to us. Also, if we're not already in touch with us, someone will be reaching out just to find out where you are in your warehouse automation phase, your journey, and see if that's something that you want to talk a little bit more about. And that's all we have for you today. Thanks so much for taking the time and joining us, and we'll see you soon. All right.
Have a great Wednesday, everybody.
Bye, everyone.